Hi, my name's Tijmen de Haan. I'm a faculty member here at KEK, both for QUP and IPNS, and I'm here to tell you about LiteBIRD. LiteBIRD is an international collaboration working on a satellite experiment to be launched around 2030. It consists of over 350 scientists from all around the world at over 100 institutions. We're primarily led by JAXA, the Japanese space agency, but we have contributions from Europe, Canada, and the United States. Our primary purpose is to measure the low L, so large angular scale, B-mode polarization of the CMB. And of course, the primary reason to do that is to try and discover primordial gravitational waves. More on that later. So LiteBIRD stands for the Lite satellite for the study of B-mode polarization and inflation from cosmic background radiation detection. We were selected as an official JAXA L-class mission back in 2019, and we're expecting to launch around 2030 on JAXA's H3 rocket. We'll be performing an all-sky 3-year survey from the L2 point. A little bit more on that soon. And the key here in terms of making modern-day precision CMB B-mode measurements is to have wide frequency coverage. So we work with 15 photometric bands all the way from about 40 gigahertz all the way up to about 400 gigahertz. When you combine all those sensitivities, we come out at about 2 microkelvin arcmin. The primary scientific objective of LiteBIRD is to measure primordial gravitational waves. And these are parameterized as with the tensor-to-scalar ratio R, and we will make significant improvements on current day best constraints, which are about 0.03, and we go to 1 times 10 to the minus 3. And to be clear on that, that is a total uncertainty. And we really promise we will get, at the 1 sigma level, 10 to the minus 3 or better. And we do that by budgeting not only for statistical errors on the tensor-to-scalar ratio, but also including budget for various known systematic errors, and also a big chunk of margin which we hold for unknown unknowns, so errors we don't currently know about, systematics that may come in later. In addition, if R is 10 to the minus 2 or greater, we also promise a 5 sigma detection of both the reionization peak and the recombination peak. In addition, we have other scientific outcomes that we expect to get out of LiteBIRD, but to be clear, the design of the instrument, the way that we're making LiteBIRD, is only for detecting R. So any other science outcomes are not driving the design and are purely nice to have. They come with the primordial gravitational wave search. So let's list a few of these by measuring the CMB, especially at large angular scales, to unprecedented accuracy. We may be able to study other fields, such as non-Gaussianity in the CMB. We will, and personally I think this is particularly interesting, is improve the measurement of tau, the optical depth to reionization, to a cosmic variance limited level. And not only is that interesting for reionization itself, but it also allows us to break degeneracies in the CMB allowed parameter space and measure things like the neutrino mass, which we should get a good detection for from LiteBIRD. In addition, we'll study things like cosmic birefringence, Sunyaev-Zeldovich effect, potential anomalies, as well as galactic science, which should not be overlooked. So about the LiteBIRD scan strategy. We are using a slightly different scan strategy than our predecessor Planck, in that we have, of course, still a sun shield that we want to point in the sun direction, so that we look always at the anti-sun direction and keep our instruments nice and cold. But we spin around with an opening angle beta of only 50 degrees. And then, because of just simple rigid body dynamics, we precess that spin angle precesses with an angle alpha of 45 degrees. And this allows us to revisit the same pixel on the sky more frequently than Planck did, and also with different incident polarization angles. And the benefit of that is clear for polarization science, which of course Planck was not designed to do. The LiteBIRD mission consists of 3 telescopes. So that's the low frequency, mid frequency, and high frequency telescopes, each of which has some overlap with each other in order to control for systematics. They're quite different, and I'll explain how they differ in just a moment. We use multi-chroic pixels, up to 3 colors per pixel simultaneously measured, and we use transition edge sensor bolometers, which are cooled to 100 millikelvin. As the very first optical element in the optical chain in all 3 telescopes is a polarization modulator, which should really cut down on any instrumental polarization systematics. Our optics work at 5 Kelvin. You can also see here some more statistics about the mass, power, and data, etc. So the low-frequency telescope uses a reflective design with a maximally large secondary mirror, which is great for instrumental polarization, as well as having that polarization modulation unit, that half wave plate, as the very first thing that the photons, CMB photons, encounter, which is also great for instrumental polarization, of course. The field of view is asymmetric, with about 20 degrees in width and about 10 degrees tall. That large field of view, of course, is good for mapping speed. You can see here various other statistics about the LFT. The mid and high frequency telescopes, unlike the LFT, which use 2 mirror, these use 0 mirrors. So this is a purely refractive design, reminiscent of ground-based experiments such as Bicep Keck. Each telescope also has a polarization modulation unit using a half wave plate as the very first optical element, as well as a large forebaffle to reduce far side lobes. The field of view is also very large, 28 degrees across, and it's a fairly simple design that allows us to have the lightest possible instrument with good throughput. Then we come to our focal planes. So each focal plane is equipped with several modules of detectors. The low-frequency telescope uses primarily, or I think entirely, trichroic pixels. So each pixel captures the light from 3 different frequency bands and sends those as 3 separate transition edge sensor bolometers. Similarly, the mid and high frequency telescope also have largely multichroic detectors, only our highest frequency band being a monochromatic one. In terms of technology, we use lenslet coupled sinuous antennas for the low and mid frequency telescopes, and we used horn coupled OMTs for the high frequency telescope. And as a rule of thumb, we say that every 1,000 detectors is worth about 100,000 detectors on the ground. And this is because, lacking any atmospheric interference, we are able to map the CMB much faster from space. And also, of course, the quiet environment gives us advantages, especially when it comes to low L systematics. The LiteBIRD sensitivities are shown here. So you can see here on the y-axis the sensitivity of each individual frequency band, as well as some schematic of roughly what the, maybe a cartoon of what the foregrounds might look like. So by definition, the CMB is flat in these units of microkelvin arc minute, and you can see that where the CMB is brightest, around about 150 gigahertz, we have the most sensitive bands, and then we have extensive frequency coverage, both at high frequencies in order to characterize the dust, and at low frequencies in order to characterize synchrotron. We think diffuse foregrounds are responsible for almost all the foreground interference that needs to be removed in order to measure these very subtle signatures in the CMB. The LiteBIRD cryogenic system uses a variety of technologies. We have these 3 what we call V-grooves, which are primarily radiatively cooled, so passively cooling pre-cooling much of the telescope, although the inner V-groove is coupled to a 15 Kelvin pulse tube cooler, which actively cools the V-grooves. Subsequent stages of cooling include a 4 Kelvin Joule-Thomson cooler and 2 two-stage Stirling pre-coolers, which keep a plate at about 5 Kelvin, which all the telescopes are coupled to as their base plate. We then use an adiabatic demagnetization refrigerator in order to get us to that coldest stage of 100 millikelvin. And you can see a schematic of that on the screen. The polarization modulation unit, as I mentioned, for all telescopes is the very first sky-side optical element. And what that allows us to do is any instrumental polarization induced by any of the optics or any of the subsequent stages of the instrumentation doesn't matter to first order because the polarization already has been modulated up to a few hertz where all that information lives, and therefore we avoid all that instrumental polarization systematic noise as well as 1 over f noise. So the way that works is that the instrument's never perfectly stable. You always have some amount of a red noise spectrum. And by modulating the polarization to higher frequencies, all that slowly varying polarization information from the large angular scales on the sky gets modulated up to a higher frequency, avoiding the 1 over f noise that's inevitably present in any experiment. You can see here a nice video of a breadboard model prototype of a rotating half-wave plate. This measurement was taken at Kavli IPMU at the University of Tokyo. Here we are in the QP lab, where I'm standing in front of our Blue Force dilution refrigerator, which gets this base plate down to about 100 millikelvin. Here we are testing and demonstrating the DF-MUX technology that will be used for LiteBIRD. That stands for Digital Frequency Multiplexing. In this technology, we take each TES and couple it to its very own LC resonator, which selects a bias frequency where that bolometer can be biased, meaning held at the correct point in its transition, and be read out. Each of these resonators is put in parallel with each other and then read out using a single superconducting quantum interference device, also known as a SQUID. And that happens in batches of about 68 TESs or less for LiteBIRD. This technology draws its heritage from ground-based experiments such as the South Pole Telescope and Simon's Array, and this is just the perfect environment to be testing this in. So currently this cryostat is being commissioned, but soon we will be putting LiteBIRD-like TESs, LC resonators, and SQUIDs in here in order to demonstrate the exact iteration of this technology that will be used for LiteBIRD. The point of having this multiplexing is that imagine having to hook up 5,000 detectors with a pair of wires each. I mean, that would be impossible, right? 10,000 wires. Just think about the total heat load that would go onto this stage, which has very little cooling power. In this case, with this huge cryostat, we have about 500 microwatts of cooling power. But in LiteBIRD, of course, with the relatively wimpy solar panels, we can't cool that much. We have only just over 2 microwatts of cooling power for the entire experiment. So we really need to reduce the number of wires that need to reach this stage. In addition, the multiplexing factor just saves on the total number of amplifiers we need, and it overall saves on mass, cost, volume, power consumption. So thank you very much for your attention. Thanks for listening. Of course, interaction is the most important part of a presentation like this. So if you're following from Cosmology from home, please do join the discussion session. You can ask me anything you want about LiteBIRD, and I'll do my best to answer. If you're joining us from YouTube, feel free to just write comments in the comment section, and I'll be watching for comments. So thank you very much.